Somebody could, yeah, if somebody could monitor the Zoom chat, because I won't be able to see it, if you can monitor that, that would be awesome. Thank you. So I'm just going to collapse the whole video thing. So yeah. They'll hear me, don't worry.
So, good afternoon, everyone. We have our speaker, Professor Shriram Krishnamurthi here from Boulder today. Shriram is one of the stalwarts of all methods and computer science education research. So he did his PhD from Rice University in 2000. And he has, since his bio is completely tongue in cheek, I really can't read off his bio, so I'm reading off this.
Yeah, no, don't worry. It's all
yeah. So he's from Brown, and he's actually known for like languages such as Python, bracket, and all this kind of languages heavily used in pedagogy, CS pedagogy. And he has won the Robert Miller Young Research Award in 2012 and 6
Don't worry about all the stuff. It's it's all good. It's all good. Yeah, thank you. Thank you everyone for coming. People in the back row, can you raise your hands, please? Okay, so I assume you can hear me. If at any point you can't hear me, let me know. And if the Zoom people, I am going to walk around a little bit. So if the Zoom people start having trouble with the audio, let me know and we'll work something out. Like maybe I'll turn my laptop roughly here, and then hopefully that works. Okay. All right. So here's what we're going to do. It's late in the afternoon, so we're going to start with a little bit of warm-up activity. Okay, I'm going to give you all tasks to do. By the way, it's a real delight. Jet, by the way, is really responsible for all of this happening. But like to be at one of the best formal methods groups in the country is both kind of awesome and a little intimidating, because I don't know how you're going to react to this talk. So I'm going to start by giving you all some warm-up work, right? So here's what I'm going to do. I am going to show you I might. This was all working in the other room. Give me a second. Sorry. Okay. So there we go. Where is my mouse? It's there. Oh, it's going over the slideshow. Oh, Lord. Okay. Oh, I have to go to Zoom. I bet that's what it is.
Yeah, that's right. Yeah.
And now I have to find my mouse again. Where's my mouse? Mouse. No, I don't want any whiteboards. Go away.
This is where they have to take human factors.
Yes, exactly. Here, hold on. I think I got it. Aha. Okay, now that I've demonstrated my competence with computers. Okay, so here's what we're going to do. I'm going to show you a formula, and you're going to tell me the values for which the formula is true. Ready, everyone? Yes, go. True. A and B are both true. And how many possible solutions are there? One. Okay, next formula. Two answers, right? Two. Three. Very good. Okay, how about this one? 0. Okay, good. How about this one? Yeah, okay, fine. But the point is, you know how to solve this problem, right? Okay, so you know how to solve this problem. So this is, of course, as everybody in this room knows very well, this is the problem of satisfiability. Okay, so satisfiability is an extremely useful tool in the modern world. I think at least half this room, I don't need to tell this to, you know this better than me. Right? And there's a whole bunch of very interesting systems problems we can reduce to satisfiability questions, right? So I built tools that do all of this. Several people in this room have built tools that do all of this and do all kinds of other things as well. So it's a valuable thing to have in the modern arsenal. And we've all seen the graphs, right? They look like, kind of like stonks go up kind of graphs, right? Where the performance of SAT solvers just gets better and better and better. Okay? Now, there are many ways to approach a SAT solver, okay? What is a SAT solver? Well, half of you know, and the rest of you are SAT solvers because you've been solving SAT faculty problems for me all along. Okay, so there are several ways to work SAT solvers. I have a particular tool that I sometimes like to use. It's a tool called Alloy. It's written by Daniel Jackson's group at MIT. And I don't expect you to know Alloy. I'm going to give you a very, very, very quick run through of what Alloy looks like. Okay, so what happens in Alloy is you write a specification. By the way, is there any chance of turning that light off? The glare is kind of high, and I think it makes it a bit harder to read what's going on. Just the front light. Don't turn off all the lights, I'll fall asleep, so. It's fine, I'll just leave this one.
Well, it's weird how the other one will turn it.
It's okay, I'll keep going. Okay, so here's the deal, okay? Oh, wonderful. No, we're gonna fall asleep. Okay, yeah, okay, thank you, thank you. So here's the deal with Alloy. We're gonna write a specification, okay? And I don't expect you to read all the code, but I mean, it looks kind of like a programming. I mean, it's not great, so obviously it's a programming language, right? It's a real programming language. So this one, we're trying to set up a binary tree, okay? So we write down the specification, and then we can ask some properties about the specification, which is the classical, like a verification problem, okay? So the nice thing about Alloy is it's completely automated. And if I click that execute button over there, right? And so pedagogically, it's nice because it feels a little bit like programming in an IDE. You click run, nothing comes and says, oh, please discharge this lemma or anything like that. It just comes back and says, no, in fact, I found a counterexample to your claim that this is the definition of a tree, okay? And if I click on the counterexample button, it shows me a picture like this. Now, why is this not a tree? Anyone? It's got loops, yeah, we can't have cycles or loops in a tree. Why else is this not a tree? Yeah, it's actually like it's got sinks rather than sources, right? Okay, so there seem to be many ways in which this is not particularly a tree. Okay, so now I can add some more statements over here, and I do verification again, and it says no counterexample found. So it's at least as good a tree as the properties that I've written. Okay. Now you notice something I just said, right? I didn't say it's a tree. I said something about as good as blah blah blah, right? And of course, if you go ask a formal methods person about this, and like they're like, oh yeah, coming up with properties is really hard, and then there's like a little embarrassed laughter, and then you move on to writing the papers. Okay. But in fact, there is a very good question of where do people like how do people figure out what properties they want from a system? Okay. That's not going to be a main focus of this talk, but it's going to be a thing that will come up once or twice during the talk. Okay. So the thing that I particularly like about Alloy, which is all just sort of the power of SAT solvers produced, sort of projected up to the human, is that I can get rid of the property. Maybe I don't know what properties I want, right? I can say, just show me some examples of a binary tree, right? And this is unlike traditional verification because the whole point of verifier is, like all of your beautiful model checkers, if I don't have a property, it just says, well, what do you want me to do, right? Here I can say, please show me some examples. And it comes back and says, wait, here's an example of something. Here's an instance, right? Here's an example of a tree. Is this a tree? Are there additional reasons why this is not a tree? Any additional reasons why this is not a tree? There's at least one.
It doesn't have leaves.
It doesn't have leaves. What else? Yeah, the left and right are both pointing to the same child, right? So there's something very powerful about this idea that we can look at examples and inductively try to figure out what kinds of properties we want instead of first knowing upfront what all of the properties are that we want. Okay, so this business about examples will be a key part of this talk, but I'm going to use this view to motivate what the rest of this talk is about. Okay, I'm going to talk about 4 things today. The first one is when I click that execute button, what do I compute? Second thing is, what do I show? The third is, how do I show it? And the fourth is going to be something about what do we write? Like, how do we write down the specifications? Those are the 4 parts of this talk. Okay, so that's the talk. That's where we're going. So what do we compute? So in some sense, the answer is obvious, right? Like this is satisfiability. We construct satisfying instances. That's what a solver produces, right? That's what you produced. You gave me satisfying instances. Okay? And that's the output that the solver produces. But it's going to be some sort of black box, right? And any satisfying instance is like legitimate. That's just what it means to be the satisfiability problem. Now, if you read a book like Jackson's book carefully, he says something much more specific than that. He says, in practice, though, the first instant generated tends to be a small one. This is useful because small instances are often pathological and thus much more likely to expose subtle problems, right? And again, everybody who's worked with these tools is sort of nodding along, saying, yeah, that sounds about right, okay? So what we did was we embarked on a multi-year project of what we call principled model finding, which is let's endow the output with some richer mathematical principle than just it satisfies the input, okay? So I'm going to spend one slide doing the like academic bragging thing, okay? And then it's okay because the rest of this talk is going to tell me how I was wrong and I have no business to brag, okay? So the bragging thing was we built a collection of systems. One of them was a system called aluminum, okay? I do apologize, there'll be like bad metal jokes in this talk, okay? So aluminum is its alloy, but it gives you min examples, okay? So it guarantees to give you minimal examples, right? Okay, and then we built another system called amalgam, which provides provenance information, publishes at major conferences, we won like paper awards and all that is very good stuff, okay? That's fine, that's the end of the braggy part, okay? But we started to read our own papers a little carefully, which I suggest not doing because it's a bit of a dangerous thing to do, because here's what we found, okay? So here is the aluminum paper, and it says, when confronted with a scenario, a user can be confident that every tuple something, 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 okay? The amalgam paper says, it's crucial that tools empower users something, something, something. Well, these are not mathematical statements, these are human statements. These are statements about how the human being is going to react to the tool. Okay, so we then did, this was like my first foray into doing sort of formal methods, human factors research, right? We went off and actually studied these principled model finder outputs, wrote a paper. We did not win any best paper awards, but it is a far more important paper, in my opinion, than the previous papers, because we actually studied this, okay? And I want to give you an example of the kind of thing that happens. So the concrete, I'm not, by the way, HCI people in the room, I'm going to skip over all the details of like, recruitment, how many factors studied, blah, blah, blah. If you really want to know the details, you can ask me about it later. We tried multiple scenarios, multiple conditions, we did some crowdsourcing, we did some student subjects, et cetera, okay? So here's an example of a problem we have our users work through, okay? So we want them to understand that reference counting is not a perfect garbage collection technique, right? And why does reference counting not always work? Anyone? DL people? Cycles, right? We want them to understand that point. So here's an example of a state graph, right? So there's a stack in a heap. The stack is pointing to various heap cells, and the heap cells have various self cycles, okay? And there's actually like also non-self cycles, I think, in this. And we're also going to show them a post state. So the post state, the stack has dropped references to some of the heap cells. It's pointing only here. So those cells are now garbage that can no longer be collected. Okay, good. So that's an example of an almost maximal model, right? It's got lots of stuff going on in it, which is not great for comprehension because a lot of superficial detail. And this is exactly the thing that Daniel is telling us in his book, right? Focus on the little examples. Okay, so let's minimize these models. And by the minimization algorithm, we get this. That's not very useful at all. Now, you might say, actually, Shriram, it's pretty useful given what you just showed me before. But if this is all I showed you, it's pretty hard to understand what's going on. Okay? And here's what we discovered. We gave our subjects the option of going back to regular alloy. And in fact, it turns out most of the participants dropped out of the study entirely. They just were like, we just don't like this tool. But it gets worse than that. A bunch of people stuck with the tool and they all ended up making the wrong kinds of edits because they over-focused on the wrong detail, which is self-loops. Okay, so users don't like it, and the poor users who thought they liked it got actively misled by the tool. This is a really bad starting point, okay? But it's also the thing that made us realize that we really need to be focusing much more on the human factors of this rather than only cranking out algorithms and proving theorems and doing performance measurements, right? So the takeaway message for this part of the talk is it's actually a very humbling outcome. And it taught us that like things that are mathematically elegant, and again, those of us who have a math training know, like we just instinctively think like, oh, minimization, like of course, how could that not be a great thing, right? It's obviously a good thing. It's not obviously a good thing. In fact, it's somewhat obviously a bad thing in retrospect. Okay, so it's kind of humbling, and the idea that these mathematically beautiful things are not necessarily good for users. Now, I will say, I don't think we are the only people who have written papers that make these kinds of claims. I'll just leave that comment over there. Okay. So that's the first part of the talk, okay, to get you all warmed up and to understand why I care about human factors for patterns. Okay, now I want to focus on the second part of the talk, which is what are we going to show? So let's think about what our goal is in showing output, right? We're going to show this visual output. The goal of showing the visual output is that our users, it's like something is going to happen in their brains, right? They're going to see this visual output, process it, and as a result of that processing, they're going to come to some conclusion that is the correct conclusion. Now, of course, when I put it that way, your response ought to be, you know, Shriram, we're not the first people in human history to think about this. Like, this is literally what like perceptual psychology and educational psychology study and have been doing it for decades now, okay? And there's actually a beautiful, beautiful body of literature here. I'm just going to flash up some names of papers. I'm not going to go into the details, but they come from all over the literature and they tell us all kinds of fascinating things. And this is the body of literature. This is actually the first paper, the Gibson paper, dates to 1955. There's a whole bunch of literature since then, a bunch of different domains that we are trying to draw on. Okay, and let me illustrate this very concretely. Okay, so in this user study, we ask people to make inferences about a blob society. Right now, when you do these kinds of studies, it's really important that you have to like prevent people's prior knowledge from becoming too active, right? If I ask you something about like, you know, society, about human society, well, you know, you're going to encode all the things you already know about human relationships. So we're going to do something about blob society, okay? So here's what's going to happen. I'm going to show you an example, and based on what I show you, you're going to try to tell me something that you think seems to be true of blobs. We're good? Okay, so here is our blob society, and here's a picture, and for those of you who have trouble reading the text, there's a dinner party, there's a blob, a meal, the blob is cooking, and the blob is cooking, okay? So in case that text is hard to read. All right, people, throw out comments about blob society. What are you learning about blob societies? Sorry?
It's collaborative.
It's collaborative. Anything else?
They cook.
They cook, okay, yeah, very good, yeah, okay, good. Anything else? Cooking is involved in a meal, anything else? They might not eat, that's not clear, it's like the back of the kitchen staff or something like that. Okay, all right, now I'm going to show you a second example from blob society, and that edge over there says parent of. Now do you learn anything about blob societies? They can reproduce, yeah, exactly, that's how you get a parent relationship. Anything else?
They enjoy family meals.
They enjoy family meals, perhaps. Okay, all right, good. Okay. Now I'm going to do one more. I'm going to show you one more example. But this one's going to be super weird, and here's why. Okay, we all know how stat solvers work, right? Because you are all stat solvers. Okay. Now, when I give you a formula and ask you for a satisfying instance, you give me a satisfying instance. It would be extremely strange if you gave me a non-satisfying instance. I mean, like, there's always like one troll in the audience, everybody else is going to but that's possible. Okay, but what we're going to do is we are literally going to make the stat solver produce non-satisfying instances. So here is a third picture, and this one is not a valid dinner party. Now, what do you learn from this? Does this add any information? What does it add? Yeah, parent has to be involved in cooking, yeah, right? Or two blobs have to cook, maybe a parent, or maybe that, we've got now two conjectures about blob societies, right? Now, by the way, I know what you're thinking, like, there's three damn blobs for wrong, okay? The point here is not about blob society, right? Remember what I started off talking about, we use the same tools for network administration, for security policy configuration, for website design. Right? So you have to think about these examples in terms of these much more interesting and important and like daily relevant contexts, even if you don't care about blobs. Okay? So notice you were now able to come up with two new conjectures that you couldn't from the first two instances. Okay? We are building on a theory from cognitive psychology called the principle of contrasting cases. And what the principle of contrasting cases says is that people learn better when they see multiple instances at a time that happen to differ in systematic ways. The principle also tells us that sometimes it's useful to show negative examples. Essentially, what's happening is when I show you positive instances, you're learning more and more, but you don't know what the fringes of the world are. You don't know when you can stop conjecturing. The negative instances are kind of an outward pressure that kind of tell you like how to scope the blob that you're trying to understand, right? That's why the negative instances are vital here, right? So this is one condition that we tried where we show you 2 positive and 1 negative at a time. Tried a whole bunch of other conditions as well. And again, lots of conditions, lots of domains, we did like, crowdsourcing and human student subjects and so on. What we learned is in this domain, the multiple examples are somewhat useful, but the negative examples are particularly useful. Okay, they really help us sharpen our understanding of the examples that we're looking at. An interesting thing, an interesting consequence was we had one condition that outperformed all the others, and it was this condition that I've written as like 2 positive and 1 positive / negative. So to explain that, have you ever tried to like look at 2 pictures or 2 documents that are very similar, and you put them in like 2 tabs and you go back and forth, back and forth, back and forth, right? What's going on there? You're using your visual cortex. Yeah, you're using your visual cortex ability to talk about it and remember what's already there to zone in on the differences. That's what this is. The third example we show is a positive example, but has a little toggle button. And when you toggle it, it gives you a near negative example, right? Now, SAT people can think about how we generate negative examples, fun technical question. I'm not going to go into it here. You can think about it and ask me later on. But the point is, you can go back and forth. And we saw some subjects go 7 times back and forth, right? Because they're trying to understand, they do that flippy thing in their brain to try to understand the domain better, right? And interestingly, this is not a thing I've seen described in the literature before. And I think it is because typically this kind of stuff has been used, for example, in like school math education, where you don't have a computer screen where you can flip back and forth. It's all like paper, right? But adding the computer to this gives us a new modality that we didn't have. Okay, so that's the second part of my talk. And here's my takeaway message, okay? So I'm going to say something really obnoxious here, right? Which is this is basically the wheel as reinvented by computer scientists, right? We don't want to learn about wheels. We don't want to go and study, circles and, coefficients of restitution. We'll just like make up our own stuff and say like, yeah, good enough, must be awesome, right? And I think there's actually a huge body of literature that's out there. I'm only myself just starting to mine. And in fact, half my time at Stanford here, and half my time was actually spent with the Ed department, the cog sci department, rather than the CS people, because that's where there's a lot of stuff here for us to learn and use. Okay. Okay. That's the second part of my talk. Now for the third part of my talk. Okay. Everyone's still with me? We're still doing like satisfiability, alloy type things, trying to do domains, etc. Okay, good. All right. So for the third part of my talk, I am going to show you a visual output of a particular domain, and you are going to tell me which computer science domain it's from. Okay, good. Everyone ready? Yes, ready? Okay, good. So here's the example. And let me just read out to you. It says philosopher, fork, left. Yes. What are we talking about? Undergrads, any undergrad recognize this? Are there any undergrads in the room? Maybe not. No? Yeah. Sorry?
Sophomore right now.
Okay, excellent. You're sophomore, you probably haven't seen this before. Sorry. Yeah, not fair. Okay, master's student. Any master's students here when it comes to this? Yeah. Oh, sorry.
Someone in the chat said dining philosophy.
They are awesome. Thank you to them. Yeah. And they've also confirmed that they can hear me that way. Okay, what were you going to say? Dining philosophers. Okay, so now, and you can look at dining philosophers. Here's like a pre-state and a post-state. And can you see the difference? You can, come on. Yeah, exactly, right there, right? There's like 2 edges over here and 2 edges over here. Okay, good. Okay, so now let's think about this for a moment, right? Like dining philosophers is a classic example of a dynamic problem, right? But we have, it's like they're state transitions, but we always have like static textbooks, right? We never show the dynamics. It's like, oh, you can kind of imagine it. So imagine that we could do a new kind of formal methods textbook where we can actually show people and have them work through it, right? They can click back and forth and look at the different states and see the process evolving, maybe even tweak the spec a little bit and try to see like, what happens when they tweak the spec. Wouldn't that be awesome? Right? That'd be so much better than the static textbook, right? Wouldn't it be so much better if we had this picture in the textbook? You look, what's the skepticism for?
Basically, I think it's a case where there's too much information in this picture.
Really? Okay. How would you prefer this picture be shown?
Basically, show this and then zoom in.
Zoom in, okay, any other suggestions?
You say total, like in one, you see the first picture and then you superpose.
You can
the second.
superimpose,
So
yeah,
you
yeah.
see clearly like the things that are kept and the things that are changing and like that's.
We've tried visual differencing, it's very, very hard. You're right, we've tried like different tricks to do the superimposing, it's pretty hard. Your intuition is absolutely right, I just don't know how to do it well yet. Anything else, any other suggestions? I mean, don't people recognize this from their textbooks? No, it's not what your textbook look like. What's your textbook look like? Kind of like that. All right, so is that better? Okay, now here is the thing. What? Oh yes, sure. Go away. My mouse. There we go. Ha! You will not trick me again. Okay, good. Okay, so. By the way, the bottom picture has exactly the same amount of information as the top picture. Is exactly the same. There's an isomorphism between the two, right? I have not done a user study of this yet, but I think it's a pretty safe bet that you're going to prefer the bottom pictures to the top one. Okay, second example. Okay, second example. I'm going to show you the picture. You're going to tell me the domain. Okay, so let me read it out to you. It says public key, private key, text, ciphertext, attacker. Yeah, it's a crypto protocol, right? What do crypto protocols look like? What do textbook crypto protocols look like? Yeah, they look like that. Yeah, exactly. Okay, so I call these Alice and Bob pictures. People call them swim lane pictures, message sequence charts beginning. Okay, so where are these pictures coming from? We have been working on a new formal methods tool called Forge. Forge is basically our variant of Alloy. We started with Alloy so we can use the Alloy syntax and the Alloy semantics. And we have now been departing from Alloy in several ways and trying to, like, in our opinion, significantly improve the pedagogic experience, right? So one of the things Forge enables is domain-specific visualizations. So the previous picture was about 100 lines of code. This one, there's a 100-line version that produces a very basic version of this. This one's about 1,000 lines of code. That's because it's actually interactive. You can click, you can hide, you can do all kinds of things to probe the crypto protocol a little bit, okay? But I claim that there's something more important going on than just pretty pictures here. And to make that point more crisply, I am now going to do another activity, okay? Here's what's going to happen. I am going to put some text on the screen, and you're going to tell me what color it is. Everyone ready? Ready? Yes? Yes? Okay, go. Hello, one person spoke. One person. Let's try this again. That was about 50%. More. You can't, okay, well, you can wait for somebody else to say black and say black the rest of the time. Okay, how about this?
Blue, red, green, red, orange. Blue, green, black.
Okay, why am I showing you this? This is an old trick in psychology. It's called the Stroop effect. And the Stroop effect is basically, I'm going to show you information on two channels. In this case, I'm giving you a visual channel of the color and a textual channel of the name of the color. And it turns out that when the two channels are congruent, you are much faster and more accurate than when the channels are incongruent. Okay? Good. Okay, that was a nice piece of entertainment. It was entertaining for me, it was hard for you. But the question is like, who the heck is any of this in the top? Well, I'm going to show you one more example. Okay, so here is the example. I'm going to read it out to you because it seems a little hard to read from the back. It says, farmer near, fox near, chicken far, and grain near. What domain is this?
Puzzle.
Yeah, river crossing puzzles, right? Excellent. And this better? Okay, so this is a pretty picture version. Okay, so there's a pre-state and there's a post-state. Okay, and obviously the picture on the, sorry, the mouse is a bit annoying. The picture at the bottom is prettier to look at. And I mean, you also like, you wouldn't want to hurt this poor like chicken over here, right? Like it's such a cute little chicken. Okay. But what does any of this have to do with the Stroop effect? Well, right, I haven't forgotten that, and neither of you. Okay. You notice that at the top in the graph, right? The picture is nothing has moved around. So in fact, at the top, it says fox is on the near side, chicken is on the far side in both pictures, which it is, right? But they're both on the same side in the picture, in the visualization. And if you look at the farmer and the grain, they've actually crossed sides, but they're on the same side in the generic visualization, right? So essentially what's happening is the generic visualization is playing a Stroop effect on you. And I swear, first time I saw this output, I'm like, what is going on? I can't, because my brain kept putting the things over where the boxes were, but the darn things were like sometimes there and sometimes somewhere completely different, right? And if you eyeball those pictures, you're like, nothing changed in my system. In fact, almost everything has changed, okay? Now, wait, you guys designed a really stupid visualizer, right? That would be a legitimate response. Actually, it's not quite as stupid as you think, because previously we used to randomly place the boxes. The problem with random placement of boxes is that as you go from state to state to state, everything moves around and you don't get any of the benefit of your visual cortex remembering where things were. Remember we talked about flipping back and forth? It's a nightmare when everything moves around. So the feature was, let's try to exploit the visual cortex by keeping all the atoms in the same place. The problem is that doesn't know anything about the model that the universe you're working with. Okay? So, I claim that something much more important is going on than pretty pictures. Okay? What is going on is that our domains have some very rich spatial information that the generic visualizer doesn't know, right? It's there in our brains, it's there in our natural language, and it's completely lost by the time we even send it to the SAT solver, much less we get an instance and try to show it to somebody, right? If you think about the dining philosophers, same issue, right? The philosopher 1 and 2 and 3, the left fork and right fork and the circularity was central to understanding the problem. The circular table is not just circular because it's like, oh, that's pretty. It's because it represents something important from a spatial perspective. When I talk about the crypto protocols, Alice and Bob, it's very important that I see Alice's message with Alice and Bob's messages with Bob. That spatiality is vital to understanding a crypto protocol as a reader. Then there's also temporal information. If you think about the crypto protocol, the order of the messages is absolutely vital. You can't reorder messages in the crypto. I mean, you can if you're like some crypto bro or something that actually breaks. But if you're like actually serious about properties of your crypto protocol, the ordering messages is absolutely essential. That is temporal information, and it's all being lost, right? So this is the problem with generic visualization. It does not understand the spatial and temporal constraints that are central to the domain. Okay? So the takeaway message here is multifold. First, the domains have evolved useful visual metaphors for whatever reason, right? If I go to a cryptographer, they will immediately understand that picture, with the crypto protocol picture shown as that. They're not going to understand other pictures. Whether it's a good picture or not almost doesn't matter, because if you want to get somebody into that domain or want to talk to somebody in that domain, that's how you got to present it. Okay? But also, these domain locations often are encoding important spatial temporal information, right? Even that circular table is showing something very important spatially, right? The third thing is something we are now working on. So Forge is built on top of a system called Racket, in which we can define domain-specific languages very easily. So we're also defining domain-specific input languages. For example, we have a language in which the only thing you can do is write a crypto protocol. Right? So the input is all cryptographic. So you don't need to know about SIGs and you don't need to know about like all the alloy keywords and all these other weird things. It's a very limited language for writing crypto protocols. Right? So the input is crypto protocols, the output is a crypto protocol visualizer. Essentially, it's an epistemically closed universe for understanding crypto protocols. We are talking about building a mini language, a very small language for being able to write dining philosophers, right? We are looking at all these little domain-specific languages so we can take formal methods and embed it in other subjects and other disciplines where they don't have to learn all of like alloy and first-order logic and modern and all this fancy stuff. They just need to learn a small notation for their language and boom, they're off with them. Okay? All right. So that was the third part of the talk, which is how to show it. Last part of the talk is how to describe systems. Now, it's kind of amazing visiting Colorado because like everybody knows what a Buki automaton is from what I can tell. I think it's like in your freshman curriculum or something like that. No, I'm kidding. Don't worry. If you don't know what it is, that's totally cool. Okay. So let me, for the two people in this building who don't know what linear temporal logic is, let me introduce you to linear temporal logic. Okay. So linear temporal logic is, we're going to start with propositional logic. Okay. And how do I know that you all know propositional logic? It's because you're all sat followers. Very good. Okay, so you know propositional logic. But propositional logic is limited. You can't say things like, well, like if there's a green light, it's a traffic signal, eventually everyone's going to get a green light. Okay. Or you want to say like, well, it's never the case that the traffic signal is going to have both a red and a green light at the same time. Or you want to say something like, if somebody gets a lock, they're eventually going to return the lock. Right? Or maybe, I don't know, if you like have a kid at home, like in my household, we write proper policies, of course, in temporal logic. So we say like no cookies until you finish your homework. Okay. All right. So you notice that all the underlined things, all the underlined words are words that are coming about from the temporal domain. So linear temporal logic is basically propositional logic extended with, there's slight variations of this, but roughly speaking, 4 operators, where we can say things like always and eventually and untils. Okay, so that's the logic. Now, it's very widely used. It's at other places, I have to explain that the roboticists have picked up on it. Here, like half of you are doing it with roboticists, so I don't need to tell you that, right? So it sort of escaped from the lab. It's no longer just a verification or synthesis logic. It's also like a robot, RL logic and so on. Okay, so extremely useful. Now, for people who are like old enough, which is almost nobody in this room, right? There used to be like intense debates about this. Like there's a famous Moshe Vardi paper, because there's always a famous Moshe Vardi paper, and it says like, CTL is unintuitive and hard to use. LPL, in contrast, is framework. It's expressive and intuitive, right? Okay, or the IBM Sugarline, which is a very nice system, by the way, allows engineers to easily and intuitively specify their designs. Sound familiar? Yeah, okay, so maybe we should test out some of these clips. Okay, so what we did was to say, well, let's check whether this is true. Now, what does it mean to use LTL correctly? I would argue that it has at least 2 characteristics. One is, given an LTL formula, can you correctly translate it to English? Okay, and the other direction, of course, is given an English utterance, can you translate it to LTL? And by English, of course, put in your favorite natural language. We did this study in English, right? Arguably, the English to LTL direction is more important because that's the common use case, right? I have some utterance in my head, right? I need the robot to do this thing, or I need the system to have this property, and I have to translate it into LTL correctly because that's what the system is going to work with. Okay. Now, you folks, of course, know there's a little bit more going on because these 2 things correspond to the syntax, but LTL also has a semantics in terms of what's called trace satisfaction, right? So there's actually a third thing, because if somebody makes a mistake at the syntax level, you want to know, is it a syntax problem or do they misunderstand the semantics? Okay, all right. So there are 3 things we need to study. We spent about 3 years doing this. We're working towards something we call a concept inventory. For education people, you know what that is. If you don't know what that is, I can tell you later on. The fun thing was we actually got about 30 experts who use LTL on a daily basis to also respond. They did a whole lot better. Okay. And what we came up with, what we now have is a catalog of misconceptions that people have about LTL. Okay, and I'll just highlight one of them to you and try to explain what's going on, right? So here's what we're going to do. We are going to vote, okay? I'm going to give you 2 options. We're going to vote on the meaning of what does X until Y mean, okay? And you can vote for option 1 or option 2, okay? Option 1 is X until Y means X is true until sometime T. At time T, Y becomes true, okay? Option 2 is the same, except at time T, X becomes false. Okay. All right. I want everybody to yell out either 1 or 2. Yell. 1, 2. Good. Okay, very good. Okay, now, let's say you picked 1. Okay. So I know a few people here know LTL. Okay. Let's say you didn't know LTL. Okay. And you picked 1 or 2. Like, how did you come to a conclusion about this? Did you like make up an English sentence, for example, like as an example sentence? or just like went with your gut more or less? Okay, because let me give you an example of an English sentence, right? Here's an English sentence. Let's talk about robot planning. The robot's motor is on until the robot reaches its destination. What do you think happens to the robot's motor when it gets to the destination? It better turn itself off. That's literally what you meant by the word until over there, right? That is interpretation number 2. Okay, so sounds like that's what we want from our logic, right? Well, let me give you another sentence, right? I don't eat cookies until I clean my room. That now, maybe in practice, most people who do clean their room eat the cookies, but it doesn't even guarantee that you're going to eat cookies the moment you finish cleaning the room at that very instant, right? Which interpretation is that? Which one do we choose? I don't know. Okay, now it turns out LTL actually happens to make a choice, and LTL's choice is everyone 1, and in fact, many people expect it's making choice number 2, right? And that's kind of a dangerous default, right? Like in some sense, 1 is a safer default than 2, but people think it seems to mean 2. So we did this study, right, collection of studies, and we're actually still continuing to do this. And more or less what we found is LTL English people generally did fairly well, except like in the cases where until, there's, by the way, there's a name in education for this. This is what's called a vernacular misconception, which is you take a word from the vernacular and you use it in a technical sense. You're doing it because you think it'll be helpful, right? But in fact, that's exactly the opposite consequence, right? It creates a misconception because the vernacular means something different or is open to multiple interpretations, like with the word up top. Okay? But otherwise, people generally did well on this. This direction, people had some difficulty, and the critical direction of English to LTL, oh my God, it was a disaster. Okay, so yeah, life is great. Okay, so we're doing this, by the way, we just finished another study now on LTLF, which is finite state LTL, finite trace LTL, right? So we have some additional data on this. And here are my takeaway messages from this part of the talk. First of all, I claim that this has pretty serious consequences for the systems that we build, people like you and also me in some cases, because our systems are assuming that people have been able to express their intent correctly and go off and do whatever we say, right? If in fact there's a correlated failure between the system under verification and the specification, you're never going to find it. I would argue that it would be much better for our systems to confirm that the property that people wrote in LTL is in fact the one they wanted, for example, by showing them concrete examples. For example, by showing both positive and negative examples of what they wrote down to confirm that's what they meant. Okay, so this is actually an active thing we're doing. We're actually, if you're interested, we're going to build an LTL tutor this summer that's going to do this kind of thing. So we're going to put that out this summer. Okay. The second claim is that, well, not claim, is we've built a bunch of instruments now that are fairly well validated. So anybody who's teaching the LTL, we can just give you off-the-shelf like quizzes. I'm going to build that into the tutor this summer, but I can just give you off-the-shelf quizzes you can use with your students. The key thing about these quizzes is they don't just have right and wrong answers. The thing about the validation, this is the thing that I was calling a concept inventory, is the wrong answers correspond to a particular misconception. So if you pick this wrong answer, I have a pretty good understanding that that's the misconception you have. So for instance, in a classroom, you can do that, they're all multiple choice. So you can do it with a clicker, you do it with a clicker and it's like, 30% of your students pick option B and A is the correct option. It's not just that 30% are wrong. You know that 30% think that until means this and not that, you can fix it right away, right? So that's the instrument that we built. And lastly, I think what we are getting out of this is also like better methodologies for building better logics in the future. Like we now have a bunch of data that can help improve the design of LTL, and we have methodologies for the next logic that somebody wants to build, rather than like sitting down arguing about X is intuitive because somebody said so. We can actually measure it and build a logic from a human factors perspective. Okay, so what I've shown you is 4 things in my talk. I started off by talking about like more principled algorithms and then told you that they don't seem to be working very well. I think we have some ideas on how to improve on this, but like we need to, our next round is going to be the algorithms are going to be accompanied not just by like proofs and performance graphs, but also by like a user study to confirm that the output was something that we cared about. Okay. The next part is I told you about the principle of contrasting cases, showing multiple examples and using the SAT solver to generate negative examples so that we show negative instances as well. The third part was about domain-specific visualizations, and the last part was about misconceptions in LTL. Okay, there's actually a lot more I think that can be done and should be done in formal methods human factors. Some of the things we've been doing is how do we train students to think in terms of properties, right? And what is a pedagogic learning progression that gets them thinking well about properties? How do we design new type systems? How can we use users in the design of type systems? How can we explain advanced type systems? So in particular, we've been spending the past 2 years working on improving the pedagogy of Rust. So if anybody here is trying to learn Rust, I would encourage you to look at rustbook.cs.brown.edu. Basically, we took the default Rust book and we've rewritten a whole bunch of it, in particular, completely redone the ownership chapter with a whole new explanation mechanism. There's a static and dynamic explanation. There are new models for explaining it. There's some counterfactual reasoning. I can tell you there's some pretty interesting things going on in the explanation over here. And they're all there online, and it's sort of endorsed by the Rust team as well. So we're not like pirates over here. So if you're trying to learn Rust or if you're trying to teach Rust, strongly encourage you to look at this. How do we find and fix misconceptions that people have in PL semantics, right? These are all projects we're working on. We've got results on, we've got tools on, off-the-shelf stuff if you're interested in. And more broadly, my training was like, semantics and algorithms and like programming languages and some degree of software engineering, right? And I want to argue that we need to combine this to be most effective with all these other things like cognitive science and education. Now, I know what you're thinking. You're thinking like, okay, cognitive science, yeah, makes sense. Okay, he gave us some nice cognitive science stuff. He played like games on us. That's great. Okay, but education is like, okay, like that's sure, turns a professor. I guess that's how he gets paid. So he's got to do that. I am going to say something much stronger, okay? I am going to make a radical claim over here. Okay? My claim is that every one of the tools that we build are actually in the education business. And I don't mean that because we have .edu domain names, okay? I claim that's true because anytime we produce output, our goal is to help our user learn something about what happened so that they can quickly, effectively make the correct changes or decisions, right? If you produce an error message, whatever you do, and the thing that is complicated in our world is when we produce output from our tools, we actually need to educate the user about two things. We have to educate them about the artifact they gave us, but we also have to educate them about the model of our own system. Right? When I give you a type error message, right, I have to educate you about like your program has this bug and I need you to fix it, but I also need you to understand something about the type system to understand like what the bug is and how to go about fixing it, right? And that is a pretty sophisticated kind of reasoning. There's actually, like in the Rust work, there's really what we call counterfactual reasoning, right? Because you need to understand the thing that Rust is preventing you from doing, which you can't do by definition because Rust won't let you. Right? Like your C++ program, you're like, oh yeah, undefined behavior, got it. If you come to Java and Python, you've never seen undefined behavior in your life. That's the concept you have to understand. And that is literally the thing that Rust won't, I can't just run it to show you a set call. That can't happen. Right? If that happens, so like you sue Mozilla or something like that. Right? So we need to educate you about your artifact and the system that you're working with, so that that is not a statement about education and like CS1 or sophomores and people like that. That's even like professional programmers. Everybody has to be educated. That's why I claim this is my radical thesis, right? Is that all of us who build tools are actually in the education business, and to be effective, we have to know something about it. Okay. So, end of preaching. If you're interested in teaching formal methods, I mean, obviously people here do, but if you're interested in some of the stuff I've talked about, Forge is our tool. It's, free, open, blah, blah, blah. And if you need to reach me, you know how to find me, which Jed already knows. That's why I'm here. So thank you. And thank you all for coming to talk. And I'd love to take your questions now. Yes.
What I was wondering is, maybe you saw.
So hold on. So I'm just going to try to repeat for the sake of the audience that's online, assuming anybody has even left, poor people. So there were a lot of good examples of counterexamples to the user, okay?
Thought about choosing counterexamples based on an estimation of what the user might know.
Ah, fantastic. So the question is, have you thought about generating counterexamples based on what the user might know? This is a fabulous question. Okay, so I think this is a very natural thing to want to try. The problem is, so here, let me tell you the stupid way to do it and why we don't do that, right? The stupid way to do it would be you first use the tool, we give you a quiz to find out what you know, right? And then we customize everything based on that, right? That would be great if you persisted through the quiz, but most people would like uninstall and move on, right? So how do we discover what it is you know in the process of you interacting with the system without us having to quiz you and make you sit down and take an exam first? That's, I think, the open research challenge to produce that kind of sort of customized experience, right? There is some knowledge about that in the intelligent tutoring systems world. It creates some anxiety in me to think about putting an intelligent tutoring system into my type system or something like that. But I think it's a very reasonable thing to think about. I just don't have no idea how to do it well. But I think that would be a very legitimate thing to do. For example, we just taught two different interpretations of until, right? Which one you understand is actually vital for me to help you understand any output that I show you. Absolutely. Yeah.
That's a great example.
Yeah.
In that case, two sentences, they're ambiguous without context. If you don't know what the robot is,
Right.
you don't know what cleaning your room and eating cookies, then you don't know those sentences don't actually capture.
That's right. So the argument is that's a good example. I think there I've distilled it down to the point where you're looking at saying, well, why don't you do that all the time? And the answer is, if I could distill things down every time, then that's what we would do. But you're right, right? Actually, Michael Jackson, by that I don't mean Michael Jackson, but I mean Daniel Jackson's dad, right? Michael Jackson, the software engineer. Michael Jackson, when I was showing him our error message research, right? He had some very interesting observations about it. Basically, the thing is, errors tend to be, the way systems give errors is they say there's the error, right? But typically when there's an error in a system, there's not actually a place that went wrong. There's an inconsistency between things. This thing and that thing didn't agree. That's what an error is, right? And in fact, one of the principles we articulated that we've implemented in our system language called Pirate is it'll show you multiple places and say, these are the parts that disagree. You figure out what the disagreement is, okay? So same way, when I produce an error message, maybe I can ask you a question like, did you mean for this thing to happen or for that thing to happen, right? Or I'm not sure. And if you mean this, then I generate this error message. If you mean that, then I generate that error message. If I don't know, then it's okay, go talk to the TA or something like that, right? So yes, I think asking a question at that moment might be just the right thing. My concern is that especially in the context of error messages, the point of getting an error message is a very anxiety-inducing experience, right? Especially in a novice, right? They're struggling, they're trying to learn about this computer stuff, right? It's not doing what they wanted to do. They're like, oh, I don't know if I even belong in this subject. What do I do? And now suddenly the damn thing is asking me questions. And I don't know what to answer. It's oh no, I think I should just walk out, right? So in some of the domains, so in a Rust programmer, I have no problem asking them questions. But novices, I think it'd be a terrible idea unless we can figure out the right way of doing it. So that is also some of the human factors affordances we have to think about. But yeah, I mean, you can see you're absolutely on the right track here, right? There's just that much to think about here. Yeah. Any other questions? Any online people? They're happy? Yes, hello.
So in a galaxy far away, I encountered a mad German guy who thought that the problem with computing was we used English words. People thought they knew what they meant. And he created a completely meaningless vocabulary. If you ever find yourself in pursuit of your work to say, we just shouldn't use until.
Yeah.
Right? And is that way?
Yeah. So the comment is this person who happened to be German who said the problem is that we use, well, not English necessarily, but vernacular. So maybe we can just use a completely invented vocabulary, right? I have several thoughts about this. One of the experiments I have long wanted to perform in Pirate is we produce these error message texts, right? I think your German friend is wrong because the assumption is people actually read them. It turns out nobody actually reads the errors, right? I think people more or less pattern match on this rough structure of the error. They kind of half read a word. So what I wanted to do was to replace them with just icons, right? And now we have emoji. When I started thinking about this, we didn't have emoji, but maybe just replace it with icons. In fact, what I really want to do is I want to replace it with hieroglyphics. So there's like 10 users who can actually read it, and everybody else is just like, oh, I got the bird thing, or I got the chair thing, you know, whatever. And then you can click on it if you really want to understand the error more. But after a while, you'll just get habituated to like recognizing the hieroglyphic, and then you'll be all good, right? So I have actually thought about some of those issues, mostly in a whimsical sense, but not entirely. But I will say, like, you know, one of the central conundrums of education in general, right, is this interplay between the concrete and the abstract, right? The concrete has the benefit that we can resonate with it easily. It has the downside that we always extrapolate the wrong things from it. The abstract has the benefit that we never extrapolate the wrong thing. That's usually because we don't understand anything at all. So there's no danger of misunderstanding anything, right? So in some sense, the use of vernacular is a little bit like using the concrete, right? You already know these words, the familiarity, but it might mislead you sometimes. If I give you this other, you know, this made up language, you won't understand anything. You certainly won't misunderstand it, but you'll be like, WTF, right? So I think it'll be an interesting user study, but that's not the direction I would go. I think maybe using like iconography might be interesting because then people can relate to it. But I think also from a programming language point of view, it makes it a little more fun. You know, like an IDE should be more fun than it's bad, right? I just got an error. I'm kind of sad. And then there's like red text blaring at me, like everything. I'm even sadder, right? But maybe I get like a cute little icon and be like, oh, it's not so bad after all. I don't know. Good question. Back there.
I would like to say that words, like now we see the meaning of icons varies in generation, for example, so.
Yeah. So the question is, would the icons also have these kinds of problems?
And, like,
This is
words like after changing like 2 years.
absolutely. So the meaning changes. I will not name a certain plant icon or fruit icon that has changed meaning over time in the emoji world. Right. I'll leave that there. So the point is, this is actually why I think emoji may be a bad idea, because emoji are now a language and people have all kinds of associations with them. And sometimes it's also not entirely clear that we share, you know, like the thanks icon is also, thanks emoji is also the pray emoji. And those are two completely different meanings, right? So this is why I don't want emoji, but I really am tempted by hieroglyphics because I don't think there's a lot of change in the hieroglyphics universe lately. I think it's been fairly fixed for a few thousand years now. So yeah. So, but or something like that, yeah. We might be there, I mean, because of us. Great. Now there'll be like an internet ISO standard for hieroglyphics because of us. Yeah. So good. Okay. Tell you what. I'm around. I know people need to leave and students have to go to classes and stuff. So what I'm going to suggest is we formally end, and then everybody who needs to leave because comfortably leave, and I'll hang around and answer as many questions as you have. Okay. Thank you. Evan, sound like you wanted, did you have your hand up? Yeah, come.